Yes, so I'm here with pyALF, and I'm first introduced the help command, and now I'm gonna import some other things. First, some helper, a small helper program, which is like print, but formats the stuff a bit prettier. And then the two things you probably already are familiar with, ALF source and a simulation object of pyALF. And here I'm gonna use the help command again for ALF source specifically. And yeah, probably most of you who are following along here or following this have used this already. So this is a class which creates an object which basically points, or yeah, here it's an object representing ALF source code. And there are a few arguments you can give it. For example, the directory. And this is the reason I always recommend people to set the ALFdir environment variable. So by default, it gets, like if this ALFdir keyword argument is not specified, it looks for this for the environment variable ALFdir and gets the ALF from, uses this directory as the ALF directory, ALF source code, or alternatively from the local ALF. I'm just leave this as is, but I want to. So yesterday I created this nematic Dirac demo, and I added it to the ALF branch, committed it to a new branch, a nematic Dirac demo. So I want to simulate on this branch, and here, so basically I execute this, and here I see checking out branch nematic Dirac demo, and here it said switch to a new branch nematic Dirac demo. If you do the same thing, you might get an issue that says I don't know this branch, and then this command here might help, which basically the exclamation mark in front is important to execute it as a shell command, so not as a Python command, but as a shell command, and get to the ALF directory and make a git pull to update it basically to the most recent, and then you should be able to execute this here again. And then if we look up here in the help again, and we don't know anything, we just know, okay, we have now here at this nematic Dirac demo branch, and we want to do something with this. The first thing is perhaps to get the Hamiltonian names, what Hamiltonians are available. And here is the Hamiltonian nematic Dirac demo, which we want to work with. And we then also want to see which kind of parameters this works with. And there is this subcommand ALF source.get default parameters, which takes as argument the Hamiltonian name. So basically, if we look at this help here, we can scroll down here and see here get default parameters, and it says ham name as argument, so the Hamiltonian name of which we want to see the default parameters. Yeah, and if you look here, so I'm p-printing it. So this was one of the imports I had earlier, that it's a bit more nicely formatted. And here we see that what are the parameters in the name list var nematic Dirac. And we can also see the other default parameters which are in every ALF simulation, like the QMC parameters and post-processing error, like the error parameters and parallel tempering and max end. And if you don't want to see this only the Hamiltonian specific, then we could write here the include. The tab thing doesn't work, but then I can show up here from the include generic. equals false. And then we only see include. Oh, sorry. This was, of course, should not be an argument of the pretty print, but an argument of the get default parameters. That's why also the tab completion didn't work. And so here we see all the parameters of our Hamiltonians. I showed how to, of our new Hamiltonian, I showed how to generate yesterday. And the next thing will be now that we know which kind of parameters we have available and what's the name of our Hamiltonian we want to simulate, we create now the simulation. There we can also look here at the help of the simulation object. And what we see is it takes 3 mandatory arguments and then a number of keyword arguments. So the first one is just the source, ALF source type object, which we created now, the name of the Hamiltonian we want to simulate, and then simdict, which is a dictionary of the parameters. So everything we want to write in the parameters file except for the Hamiltonian name belongs into this dictionary. And then we have also a number of default things, like, for example, what kind of simulation do you want, MPI or parallel tempering or so on, and which, like, with how many OpenMP threads we want to run, and also which kind of machine, like which kind of compiler we want to use, in this case GNU. So this is like the machine argument for the configure sh we can define here. And if we do this, like, we get automatically this simulation object created, and with the get directories method, we see that it automatically generates a path to a folder where the simulation will be started, and with get directories you can see where this is exactly. And then we compile according to what we specified up here, which will take a moment. And then after that we run. So this is the only simulation I will run here, because here I specified only with the CPU max parameter, I specified to run 1% of an hour, which is like 36 minutes. And yeah, so it takes a moment until the compilation is finished, and then I will run the simulation. And afterwards, I have here this method with which I can look at the info file. It's always a very good idea to look at the info file after finishing the simulation, to see if everything is stable. And then we get to two things Johannes also showed yesterday with the check warm up and check rebin. We can look at warm up and autocorrelation issues. So the simulation, the compilation has finished. Now we simulate for 30 seconds. And here it also says resuming previous run, because I already simulated already with these parameters. So it pyALF realized that there was already a simulation and renamed the conf out to conf in. And now the simulation is finished, and we have here the info file, and we see here the info from multiple simulation. Here the first simulation with very good precision. Actually, the precision is like, these numbers are so low that it would make sense to increase nrep to a bigger number than 10 to save to fewer stabilization steps, because it's not necessary to have so many stabilization steps, which will speed up our simulation. But since this is only very short run for demonstration, it's not a problem. So for the first simulation, we produced 48 bins. The second simulation, which produced 49 bins. And now we can look at these bins. So with this check warm-up argument, we look at the skull and icing. So this is like the order parameter, and this is the X component of the easing spins. And if we execute this, we will get a time series of our bins and see whether we are warmed up. And this looks pretty good, like we don't have any drift or so. So it also helps, like this widget automatic creates a fit, which are these red lines through all the dots to see if there's a significant, like to help to see if there's a significant drift in there. And this dotted line is the average over all the bins. And then, for example, if I can increase here the end skip of the parameter files to, for example, 5, and then it updates all the fits and highlights which points are actually will be included in the analysis. Yeah, and the same again we can do with the rebin. Here we have the error analysis versus the number of rebin steps for recombining multiple bins. And so with rebin 1, it looks like that we very much underestimate the error, so we should probably increase to something like, I don't know, here 7 or so. So we put here 7. And then when I tested it yesterday, I was a bit surprised because usually it should update this line here and put it over here. And then I looked here because like these also here have a log here that tell me what happens. And if I look at this log here, then it says something here, runtime error max X must be a sequence. And then I realized that matplotlib somehow changed something, and I will then soon have to update it here. So I already know what I have to do. I basically have to just add some square brackets here. But that's what logs are for, to see when something bad happens, that we know why it happens. And that's that we can fix it. But now I just have to re-execute here, and I can see that now with the nrebin here at 7, I seem to be not underestimating the error. Here for bigger nrebin, it gets a bit chaotic because then I only have my actual bins are very few, and then I will dismiss a lot of data. So that's why back here it gets a bit chaotic. Yeah, so this is just like the workflow for a single simulation. And here what I did yesterday was then a series of simulation of 4x4 on a 4x4 lattice with MPI and 8 MPI processes. And here I used Python's list comprehension to write this here in a list, like here with the square brackets you can see here. And here, this is a list comprehension. Like an easier example for a list comprehension would be, for example, this line here. Here you can see that with this list, I turned with this list comprehension into this list. This is just to flash some features of Python. And then here are the according directories and this where the simulation occurred. And here, if I want to execute this, I would run all these simulations, but I said that I want to run each simulation for 1 hour, which I won't do here because this would be a bit long. But I can still look at the info files I already increased. And so this is the main reason why the files I sent you are 2.5 GB, because here I have about 700, between 650 and 700 bins for each of these simulations created, and they are with time displaced measurements. So that's why we have so much data here. And yeah. Anyway, I forgot to mention, I think in the beginning, if there are any questions, anything is unclear, please interrupt me. Because I'm not, I have the feeling that the way I'm doing things is not always super clear to everyone. Yeah, but after this, like running 4 normal simulations, after another, I showing another feature, which is running multiple parameters in parallel, which we can do with ALF. So here, instead of this of a dictionary here, I created here this list. I can demonstrate perhaps if I just copy this out here, how this list would look like. If I just put this here. So this list here is basically like a list of 4 dictionaries. And this I inserted here to create here the simulation object. And now if pyALF sees as here and at this point here a list, it first thinks that I want to do a parallel tempering. So this is like this thing where we execute, where we exchange configurations for different parameters. But I want to for independent simulations in parallel, and so I add here this keyword argument parallel parameters equals true, and now I simulate 4 parameters in parallel. And now I have one simulation object which has 4 directories.
Sorry,
yes.
Sorry, that NMPI is the number of cores you use?
Yes, yeah, it's a bit of a large number. So this is, is a bit of a large number for using on a personal computer. This is actually like on a so-called Jupyter Hub I'm running here. No, not I'm running here, like I'm running on some server, which actually is in Würzburg. But what happened now? Yeah,
Let's make it clear. Is it the number of threads or the number of cores? Because
what do you mean? Like it's the number of MPI processes I'm using. I want to use.
If I have in a given computer.
So it's not like this is not suitable to run on a personal computer probably, because it's like you need a machine with 32 cores to run this meaningfully.
Okay, thank you.
But yeah, the data I created this way is already included in the package I sent you. So this is only to demonstrate how to do this. And here, so I have here this 4 directories, and now importantly I have to recompile because I switched from a normal MPI run to a parallel parameters feature, and this is a compile time parameter, and therefore I had to recompile. So yeah, if you change a compile time parameter, you have to recompile, of course. Everything you write in one of these dictionaries is not a compile time parameter, but for example, if you want to do MPI or no MPI or parallel parameters or change, of course, your compiler, that's a compile time parameter, and then you have to recompile. And this was the case here. So I recompiled. And now I actually didn't run this simulation in this notebook, but I said I want to just copy here to like only prepare the directories for this simulation and copy the ALF binary into this directory. And now I have created here this directory where it copies here copied here this ALF binary, and I can just for example execute this ALF binary in the shell or with some queuing system in some machine without needing Python for that. And still after finishing the simulation, I could look at here at the info files and see that everything is in order. All the stabilization is actually more than good. And I've created a large amount of bins. And the same thing I did for 8x8 and also copied the binaries to the new directory for 8x8 size and started the simulation. And then here you can see that actually the info files are incomplete if I look at the info files. So here it starts like the stuff that's printed out after the finishing simulation. So I actually have two finished simulation and unfinished simulation in the same thing because the simulation was cancelled because of reasons before it finished, and then ALF didn't print out these details I have, for example, up here with the precision and so on. Yeah, just a note, side note. Yes?
Can I finish can I stop a simulation in the middle and still extract the bins it has already finished?
Yes. So this will just work fine. The only the main downside is now you can also resume the simulation. Like here I resumed also the simulations with the conf out files. The only downtime right now with ALF is that we don't know whether the precision was any good of the green functions, and we don't know the details about the acceptance. But apart from that, it should, except if it's finishing like in the very few seconds per bin. If it's even seconds, it's probably a few milliseconds per bin. Where it was just writing the bins, then these bins could be corrupted, and then you have a problem.
The
but
bins
except
can
for
take
that,
very long time.
Huh?
I mean, if somehow the bins take quite some time, like 1 minute per bin, and you stop in the middle of a bin, then you get a corrupted file of the simulation. Is there a way to fix that or remove the corrupted bin?
I mean, usually writing out the bins is only done like once per sweep. No, once per n sweep. At the end of the bin, the bins get written to the disk, and this is like in a very short time. So if at this point ALF crashes, then your bins are corrupted. If you have plain text bins, you might be able to repair it. If you have HDF5 bins, the writing is so fast that it's very unlikely that it will crash in this moment. But if it does, then you really have a problem. Then your bins are kaput. But yeah, that's very unlikely to happen. It's just that everything that has been gathered since the last bin was written has not been written to disk, and this is lost. But apart from that, nothing is really lost. Yeah.
So it is okay to stop it when you're updating the Monte Carlo, and it's not okay to stop when you are just writing the bin into the disk. Is it true?
Yeah.
Okay.
But yeah, as I said, writing the bins is just done in a few milliseconds per bin or so, and then it's not really like you have to have very good timing to fit to hit this exact thing. Anyway, so now the 6 and 8, system sizes 6 and 8 are actually simulated outside of this Jupyter notebook, and 10 I simulated inside the Jupyter notebook. And now I perhaps want to resume a simulation. And now it says, okay, I prepared this directory and so on. But then I get a crash, and then it says ALF is already running on the previous, or the previous run failed. And this was because I also had here a simulation, and then the Jupyter hub shut down, and the simulation stopped in the middle, and then I have this running file still here, which gets created at the beginning of the simulation and deleted at the end of the simulation. And now, like if ALF gets unforeseen canceled or so on, or stops or crashes, then you should intervene manually to see what happened, what went wrong. And if you're sure that everything is okay, then you can delete this this file, and then you could run this again. But I don't want to run this now again. But now I could run it again. I can still take a look at the info files, which are of course incomplete because the run was canceled. The simulation were canceled. But now that we have these simulations, so now doing for each of the simulations sim.analyze and sim.check warm-up and so on is a bit unhandly, first of all. And second of all, if, for example, I did this analysis somewhere else and did the run somewhere else and now want to analyze, and I just have the files with the Monte Carlo data and I want to analyze them, then I'm switching to this other notebook. Then I have here this first of all this in this utilities sub package basically of pyALF. I have here this find simdirs function, which finds all directories which contain a file data.h5, which are the HDF5 bins. And now with this list of paths containing all my data, I can now start the analysis. And the first step I will do, I will define some custom observables. For this, I need this NumPy package, which is a numerical Python package for linear algebra and so on. The first, pyALF has this feature for custom observables where I define a function with these functions, I can define observables which are derived from observables with the normal observables that are measured during Monte Carlo. And here, for example, I have a correlation ratio. So this is actually it's more like it's of course. All right. This one here. So it's 1 minus some correlation function at a k point plus delta, where delta is this one or usually the smallest lattice point on a lattice, and divided by this correlation function at this k point. And so this is, and this calculates out of this observables. So ops are the Monte Carlo observable of a correlation function, which so it's it has as indices the orbital the two orbital indices, the number of time slices, and the number of unit cells. And then the background, which has number of orbitals, which is a one-dimensional array as index, the orbital index. And then also the sign, the number of orbitals, the number of tau slices, the delta tau step, and a lattice object which contains all the Bravais lattice, finite size Bravais lattice information. Yeah. Oh, yeah.
How do I tell him what directories to look for when I'm getting the list there's at the beginning?
Here, I just say it looks for all subdirectories of my current directories which contain data.h5.
Yeah, but okay, but like for me it finds also the ones that I run like in the other days.
Because
I'm running everything together. Like
yeah.
Yeah, okay, it's not the optimal thing, but
then you have to do something else. Then you can, for example, do something with, I don't know, from log or log. Then you could, for example, do something like this, like make it a bit more precise than that, but in principle something like to find. That's not.
It was like I wanted to import all the ones starting
anyway, like you have to somehow then filter this list perhaps.
Yeah, okay, but I do it probably not in the find sim directory, not in the dot find sim command, but like I do afterwards to my list, I do some filtering. Yeah, so I filter the list that I get. I thought there was some built-in thing for okay, thank you.
Yeah. Yeah. So these are the variables, all the a function is given if I say I want to this derived observable is based on a lattice type observable, so on a equal time or time displaced correlation function. And then we do here we basically calculate this thing here. I won't go into detail here because this will take too much time. But if you have questions about this, you can, like specific questions about this, you can ask them, or I can explain it perhaps later. But now I think this will be out of time. And then I also have here a function which takes a scalar type observable. So this just is the observable, the obsvec type of this obsvec type observables, sign, and nops is the length of this observable vector. So like earlier, yesterday we created this M type observable, which had the order parameter and the square and the order parameter to the fourth power, if you remember. And this we can use here to calculate this Binder cumulant here. Of course, now we only have the functions. So something similar we can do also for the susceptibility, or to calculate a gap, the fermionic gap out of the time displaced screen function. So here's the time displaced screen function for high temperature. It behaves something like minus minus gap, exponential of minus single particle gap times tau. And here we can do an exponential fit, and then for each k point, and then get the dispersion of the single particle gap. And now, like these functions now, so for of course now we have just some functions, and now we have to tell pyALF how to combine these functions to get observables. And now, for example, we can use this RK observable, this RK function here we defined up here for correlation ratios, and say, okay, this is based on the Ising Z correlation function, so the spin correlation function of the Ising field, and we name this new observable R_s. And now it will give here, when I then feed this dictionary here into the analysis, it will feed the correlation functions here through these variables into this function, and calculate here this correlation function based on this correlation ratio based on the Ising Z correlation functions. Similar we can do with the time displaced correlation function, and this is then something like a correlation ratio of a susceptibility. Yeah, here we define the Binder cumulant based on this function we defined earlier, and here susceptibility, and here the gap, which is calculated out of the time displaced green function. So with defining all of this, of course, we first need to define the functions we have up here. Execute all the cells, and then we fill here this custom ops dictionary with these definitions. And now we first can again do this kind of check warm-up. We can import it directly from pyALF, and then do the same thing, but now also with our defined observables. And now I sent it here all this list of the directories, and now I can go here through this through my simulations, and for example go here to the 10x10 simulation and see what the warm-up looks like. And here we can see we should at least go to nskip 3, and then yeah, at least here the RS, RK, and B looks okay. The others should need some more time to warm up, but I'll stay at this nskip for now. And here also we should increase the nskip. Here also. So this looks better. And now we could do the same with rebinning. Here we are relatively deep in the ordered phase. That's why we basically have very low dynamics, and that's why the rebinning suggests that we have extremely long autocorrelation times. But yeah, I mean, you already know this, and I don't have to be super precise, so I will skip this now to not make this exact. Now, before we do the analysis, we can also tell our analysis a bit of the symmetry of the model. And here we can tell that our model has a rotation symmetry, like a C2 symmetry, so which is composed of out of the identity and out of a rotation by pi. And if we say these two these two symmetries, our model has these two symmetries, then I can give this to the analysis, and then it will apply the symmetries to all our correlation function as an improved estimator to get better results. And now I will execute the analysis for all these directories I found at the beginning. I will not do the analysis for the time displaced observables, because that will take too long. I will still use the time displaced observables to, for example, calculate the gap and so on, but I will not analyze the plain time displaced green function, for example. This way our analysis will go much faster. And after we finish this, we can use this function load results to load the results of all our directories. And so here it says, it showed us how we loaded all our results. And we can look here at this results object, which is this a Jupyter node, a pandas data frame, which is like a table. Each line, each row is one simulation, and then in the columns, I mean, you saw this before, most likely, hopefully, are first the parameters, and then all the other results, which are truncated here. So here with this dots, we only see the beginning and the end of all our columns, because we have in total, if we scroll down here, we have here 89 columns. But assuming we know that so we know that our order parameter is m skull, and we want to, like, m skull 0 means basically the index 0 of our of this m skull observable of our observable named m, a scalar observable named m. And here we will plot with matplotlib this m versus with its error versus the h, which is the transverse field for our 4 different sizes. So here we filter our results for system size for each time in this, for each iteration in this loop, and sort them by age, and then plot for each filtered list age versus the order parameter, and see here this it's not a kink, it's here this jump is because for L equals 4 and age 3.0 we have 2 simulations. The one very short simulation I showed in the beginning, which is with lower beta, and therefore I have 2 different results here. And what we can also plot.
And why don't we see large error bars if there is such a difference between the simulations?
Because it's they are both probably accurate. I mean, I also was not very rigorous for the warm-up, so perhaps the n-ribbon is too small.
Okay.
But the main reason is actually that one of them is simulated with beta 16 and the other one with beta equals 4.
Okay.
For 2 different temperatures. So this is the main reason why these 2 are different. So, and here I don't look at beta, because all the others have beta, like L equals beta equals 4 times L. So they pretty well resemble the ground state. I know from experience, otherwise you should one should like confirm this, of course. But here, I think this one of these. I think this point is the one with the lower beta, and therefore.
Yeah, I see. So it's not a Monte Carlo error, but a different Trotter error.
Exactly. Yeah, no, it's not. It's not different Trotter error. It's different temperature. Different temperature. Different beta. Different temperature.
Ah, sorry. Okay, thank you.
Yeah. And now, as a next step, we can also plot here. Of course, I mean, I'm skipping here a lot of the details from how we can do nice or not so nice, but efficient plots in this case with matplotlib. But here I'm plotting here these 3 out of our custom observables, the 2 correlation ratios, one of the susceptibility and the other of the equal time spin correlation function, and the next one of the Binder ratio. And these have the property that they are so this renormalization group invariant quantities have this behavior around a critical point. And long story short, for different system size, they cross here at the critical point. And here I can see that my critical point is around 3.1, 3.2 or something like this, which all 3 of these RG invariant quantities show more or less in the same way. And then I can do a data collapse with these things by, since they're renormalization group invariant, I only have to rescale the x-axis, and then I can play around with it a bit and see that the best one I can see so by eye. And with the system sizes, of course, the system sizes are much too small to do a proper data collapse or anything, but these are sort of collapsed, at least here and here a bit, with if I plot here the RG invariant quantities versus h minus 3.15 times L to the power of 1.4. And here I have done a little bit of found a critical exponent, which is pretty nice, no? That, especially considering I only did very crappy simulations. Well, no, not very crappy, but I didn't put so much effort into it. And now, if I want to look a bit more at the other stuff of the data frame, the first thing I like, because this data frame is so big, I can't see actually what all the columns are. So here, this way, I can print all the columns separately. And here I can again look at the index of the different rows, which are by pyALF basically just named the source or of the directory where they are from. And now, for example, if I want to look at this one column which is the 10 times temps simulation for temp 0 is out of this array of 4 simulation the lowest one with age 2.5. This is pretty deep in the ordered phase. And if I look at this is just then one object containing all the parameters and all the results. And here, if I look up here, for example, I have something called Ising Z underscore EQK. So this is the equal time Ising spin correlation function in K-space. And this has the shape 1, 1, 10. So the first 2 indices are the orbital indices. And since we have only one orbital per unit cell, it's just 1, 1. And the other index is the unit cell. So we have 10 by them, 100 unit cells. And if we look at this like this, then we have here, I mean, the values look like this. And so I will create a lattice object from, so here, if we look at our simulation, we can also look here again, the lattice. So each observable has its own lattice, and this Ising set EQ observable has this lattice. So here the L1 and L2, which define the size of the lattice or the periodicity of the lattice, and the A1 and A2, which are the primitive vectors. And with this, I can create this lattice object. Of course, I first have to import it and then create the lattice object. And then, for example, these are the K points. And now there's this small helper function in the in this lattice object with which I can do a two-dimensional heat map plot of this correlation function. And here I see like just a very extremely sharp peak at 0, 0. That's because we are deep in the ordered phase, in the ferromagnetic ordered phase, which is not so surprising. At least if I took more time to explain what kind of model we are looking at least. And now we can do exactly the same, but now for the temp 3. So for the fourth parameter in this list of 4 parameters, we simulated in parallel. And here we can see now we are more in the disordered phase, and we can see also if we look at the scale that this is like a very shallow. So we still have a maximum here, but it's pretty shallow. And there we're not ordered anymore, contrary to here where we have like look at the scale here, which is 50, and here's the scale 3, and it's basically more or less flat here. And now to conclude, I can also print the fermionic the dispersion of the fermionic gap I calculated by fitting the time display screen function. And here I can see, like, to remind you, what we simulate here is a Dirac system, which has at a critical point. So let's start here. Here with H 4.0, we are in the disordered phase, and we have here these Dirac points, and it's not so well to see the way this is plotted here, but here we basically have the isotropic Dirac points here. And now if we decrease H, the Dirac points begin to move along this and this direction. And here we can see, I mean, it's not that easy to see, but here we can see that the values here and here are smaller than here or here, or here and here they are smaller than here or here. So this is becoming anisotropic. Yeah, because of this nematic transition. So yeah, actually we have 2 point, like, since so we have a spontaneous symmetry breaking here, and like from this data alone, I can't tell you, but you have to believe me that because we do MPI, and some of the cones move like this in this direction, and some of the cones move in this direction in the MPI, and we simulate 8 of them in parallel. It looks like a broadening of this Dirac points, where actually we have some of the Dirac points moved in this direction and some of the Dirac points moved in this direction. We see the average of this. But yeah, that's what I wanted to tell you about pyALF. And I think, yeah, I'm pretty good on time. So now, are there any questions?
I would have one. If you would be on the honeycomb lattice where there are two sites per unit cell, then the structure factor, the static, the Fourier transform of the static correlation function of the equal time correlation function wouldn't be periodic in this Brillouin zone, but in a larger extended Brillouin zone, which is I think twice as big or something like that. I don't remember. Because of the Brillouin zone represents the periodicity of the triangular lattice, which spans the unit cells of the honeycomb lattice. Now, my question is there an automated way to calculate the extended Brillouin zone and to visualize the structure factor in the extended Brillouin zone? Because I saw. Sorry?
Just finish your question, sorry.
Because I saw that there is a sum SZ eq, which is the sum over the orbitals. But what is sum? I mean, when you
sum in this main it is in this context it's the trace over the orbitals.
Okay, so it's not that. Because when you calculate the full, I mean, I saw that you separate the static structure factor into separate matrices depending on the orbitals.
Yes,
that is indeed periodic in the normal Brillouin zone. But to calculate the full structure factor, you have to combine them with phase factors depending on the size of the unit cell.
exactly.
So there is no automated way to do that, right?
Not yet. So there's work. There's actually this a merge request for this for ALF itself. It's not in pyALF or not yet, but there's like if you look here at ALF at the merge request, there's here the extended zone scheme for multi-orbital. So there's work in progress for this, but it's not yet there.
Okay, thank you.
Yes.
I have a question. Since there are many observables we can check in the like after the analysis, is there a place that we can look at what these observables are and what they mean? Because as I read the documentation of the ALF, there are a list called predefined observables, but it seems that those observables defined in Fortran is like somehow different than their keys in Python.
I mean, they are of course the same observables because Python only uses what is given to them.
Yeah,
like the format is a little bit different, but
yeah, I would like to know the keys and what the keys mean.
I mean the keys. I think there's no explicit explanation for this, but let's look at sorry here. So basically, I mean the icing X skull is like this part, for example. Like if you look at the scalar observables, this part is the same. This you know from the Fortran part. And then we have here 0, like for example here 0, 1, and 2. If you have like a vector of different values in one scalar observables, and then for this you have here the expectation value and the error, and here of the sign of the same observable. And then for the equal time observables, or also for the time displaced observable, you have here the thing in k-space and the errors in k-space. And for each of those, you have first the orbitals and then the unit cell as indices. And then the sum here is the trace over, is the same thing, but traced over the observables over the orbitals. And then you have also here this lattice, as I shown you, that contains the A1, A2, and L2, L1 and L2 to reconstruct the Bravi lattice. Yeah, does this help?
Yeah, I think is it going to be better if we can have like a list of this case and what they represent somewhere in the web page, so that we can check what to find, like we'll know what to find out and what to call for.
Yeah, it's somewhere, yeah.
Because
Yeah.
like if I only read the names, so for some observables, it can be quite hard to get.
I mean, the observables themselves are kind of like the first part is kind of on the Fortran side. And we wanted to, like, we added the infrastructure to add descriptions, but no one added a description for them so far, basically. But yeah, so are you more interested in what? Yeah, I guess so. It's not perfect. Yeah, I guess it's summarized like this. Yeah.
Thank you.
And thank you for the suggestion.
Perfect. So, other questions? Zoom audience? Anybody there? Yeah, if not, then we can finally thank Jonas.